Welcome back to ECE 442-542. You're just getting back from a break, and I'll greet you with the next time we meet will be exam number 2. And exam number 2, we will have a review session. I guess that's the next time we meet officially. So we'll have a review session at 7 o'clock tonight after this class. And just as a reminder, homework number 4 is due tonight. And there are some extra videos / lectures if you want to maybe be helped on problems 1A and 1B and 2B. This isn't a, never mind, I won't go on with the 2B or not to be, but we have zero order hold by hand and a state space form of zero order hold, and we'll try to go through maybe some of that in the review session. The exam, as I said, is on Wednesday of this week, and there is now a different transform table available to you if you want. This might help you if you're comparing or if you're doing the zero order hold equivalence and you want to see a S-domain expression and what that immediately gives you in the Z-domain. There's now a table that contains those two column entries in the same row, and that maybe is quicker when you're looking at the Z transform of a Laplace transformed quantity, if you've now done the partial fraction expansion in the S domain. I want to cover a fair amount in today's class. We'll quickly go over the process for exam number 2. Then we will summarize the discrete equivalent integration or numerical integration strategy. So I left off a word there in the form of a table, and that's the substitution of replacing S with some expression in Z if you're dealing with transfer functions. Then we will look at doing that same kind of operation or strategy in state space systems. And that will then actually be what you'll want to copy for problem number 5 on homework number 4. We'll hopefully go through the backward rule. We'll look at the forward rule of how do we find formulas in terms of A, B, C, and D formulas in the continuous time that we can immediately plug in to obtain a phi matrix, a gamma matrix, an H matrix, and a J matrix for the discrete time state space representation. And all you'll have to have besides A, B, C, and D is the sampling period, capital T. And you can find that, capital T, by examining the eigenvalues of your system matrix in continuous time and finding the fastest one of those and say, oh, I need to sample 30 times that. Boom, now you have capital T. That gets us down to then summarizing the forward, the backward, and the bilinear, or Tuston, or trapezoidal. That goes by 3 different names, and I think in MATLAB they use Tuston for the type of C to D operation that you want to use with that function C to D in MATLAB. We will then go through a pole zero mapping a little bit more carefully than what we have before the break, and we'll also talk about Z at I, zeros at infinity, and I sent you an email hopefully giving you a few pages as a hint as to why, if you're doing this mapping of the zeros at infinity to these numerator factors, Z plus 1 in the discrete equivalent, why is mine not looking or giving me exactly the same thing as MATLAB does? And the reason is because MATLAB maybe doesn't map all of those zeros at infinities into Z plus 1 factors. If you had 2 zeros at infinity, MATLAB may only map one of those into a Z plus 1 factor in the numerator of your discrete equivalent. And that gives you certain nice properties relative to implementation. So I was hoping maybe I had implementation issues, but I don't in that description. But due to implementation issues is why you might want to vary or reduce the number of z plus 1 factors in your discrete equivalent. And we'll try to get to that if I would quit talking. Exam number 2 process. You can have 2 sheets of notes in addition to transform tables. And now you have 2 transform tables, and actually maybe I will go ahead and eliminate the or, and you can bring both if you feel comfortable with both of those tables. One is a new one under exam number 2 material, and that compares the S domain and the Z domain in the same row so that you can quickly do that. That one, though, is written in terms of z to the minus 1s. But you can quickly, I think, map that into polynomials in z by multiplying by the appropriate powers of z in a expression that gives you 1. So you might multiply it by z squared over z squared, and that will give you the appropriate transform in terms of z. Or you can now connect those two maybe with your exam number 1 transform table, which is 1 page in the D2L unit covering the exam number 1 material. That means you'll have maybe 5 pages, but 3 of those will be one-sided. Does that make any sense? You'll have 2 double-sided pages of notes, handwritten, and then you can have these transform table pages. You might want to bring a calculator in case I give you a 4x4 matrix with complex poles that you have to now find phi for. So you're doing the inverse Laplace transform of SI minus A inverse for joking. But if you're listening to this, maybe you can't see my eyes, or I'm giving you the look that maybe you're used to seeing in class. Well, you'll just have to read that through my voice and tell that maybe I'm not quite being as true, I don't know, I'm being ornery, I guess, in saying that. But you'll need something to write with, but you can't do any of the others. You can't have your cell phone out, and I'll try to turn mine off this time before the exam. The computer, you can't have that. You can't have any more course notes. You have plenty in your 2 pages of notes that you can make yourself. No textbook, since we don't have a textbook for this class, but we do have resources. No calculator sharing and talking or looking around. None of that is allowed. That's the exam 2 process. Are there any questions on that? That should be consistent with exam number 1. You just have now more pages of material to bring and know how to use going into exam number 2. Let's get into the material. And I'll quickly scroll through this to get us back from break, and then we'll slow down and walk through problem number 5 of homework number 4 on this state space discrete numerical integration discrete equivalent. In these numerical integration strategies, we're really trying to find a capital H of Z from an H of S. And last time we looked at deriving these 3 different Z-domain expressions that we can substitute in for the S value in a given transfer function, H of S or G of S. And these are the 3 different Z expressions, one for forward, one for backward, and one for trapezoidal, bilinear, Tuston. It goes by many different names. Bilinear meaning it's a quotient of 2 linear expressions in Z. But those you probably will want to have on your crib sheet in some form so that you can use those given a G of S or an H of S. And these are for scenario number 1 for the numerical integration discrete equivalence. What we want to do now is can we use that knowledge or insight that we have for these mappings or replacing S with Z functions to go from an ABCD, so now if you're listening to this, we're learning our ABCs. That's ABCD is in the continuous time. We want to now go into the discrete time, and now I'm mixing Greek and English, but we have phi, gamma, H, and J for our discrete time state space representation. We want to now find a phi that might be a function of A, B, C, and D, and the sampling period, capital T, where X is our state vector, and that could be 10 variables tall. It's 10 by 1 if that's the case. It's always one column. We might have an input that I'm saying is given by this signal E, and the output, now hopefully this isn't confusing, but this is assuming that we're now trying to find a discrete equivalent for maybe the controller, where the input to that controller is the air signal E, and the output of that controller is the input U to the system. That's why U is the input in this description. Let's now try to derive some of these relationships for phi, gamma, H, and J. And this is the concept. This is the conceptual version of what we're trying to do. We're trying to now find phi that might be a function of A, B, C, D, and capital T. What does that function look like? And it's going to look different for the forward, the backward, and the trapezoidal. Each of those will give rise to different formula expressions for phi, gamma, etc., H and J. That's our goal. We want to find what is phi in terms of A, B, C, D, and T, what is gamma, the input matrix in the discrete time setting, in terms of those same matrices, and T is a scalar. It's going to be multiplying these matrices, and you'll see maybe AT a lot, but just remember that T is a scalar, A is a matrix. BT, B is a matrix, T is a scalar, etc. I was going to just go through the backward, and then I thought this is kind of tedious, so let me go through the forward first quickly, and then you can kind of get the hang of it, and then we'll slow down and walk through the backward numerical integration strategy. The very first step that we're going to do for all of these is to actually Laplace transform the blue A, B, C, D formulas. And we're going to neglect initial conditions because we're really just interested in the dynamic relationship, not a solution. We don't need to worry about the initial conditions. And I hope that you can now take these matrix formulas of x dot equal ax plus b e and u equal to cx plus de. You can take that into the frequency domain or the S domain by Laplace transforming. The derivative is just S. S is a scalar. That's the complex frequency variable. Capital X is this 10 by 1 vector of Laplace transformed state variable components. A is our 10 by 10 matrix, system matrix in this case. It's constant. B, if we had one input, it would be a 10 by 1, etc. This is now a frequency domain representation, and we start here for all of these approaches, the forward, the backward, and the trapezoidal. What did we do before? When we were in the transform or transfer function, when I gave you a g of s, and you would need to then hand me a g of z, how did you give me the g of z back? What did you do? If I said the forward approach, you would simply replace every s in that g of s formula with z minus 1 over t. Here, s is located two places. One is the argument of these. We don't need to worry about that. That's just telling us we're in the frequency domain, the Laplace domain. We really just need to know or worry about the s that's the coefficient in front of the x's, a's, b's, etc. And we only have one s sitting in this whole collection as a coefficient. And now what I want to do is replace that s with z minus 1 over capital T. T is just a number, that's a constant, and z is a complex frequency variable, and 1 is a scalar. And I've tried to, well, here's the first step. I don't really need to worry about the output equation because it didn't contain any dynamics, so it really doesn't contain any s's. But the dynamic relationship, now I replace s with z minus 1 over cap t, and the right-hand side is exactly the same, except now I want to go into the z domain, so my arguments now magically change from s's to z's. But that's just because I know that I'm now converting from continuous time frequency domain to discrete time frequency domain. The important part is to replace the s with this substitution, z minus 1 over t. I can clean that up slightly by simply multiplying both sides through by capital T, and I've tried to keep the T black so that you can see it, but T is a scalar. A and B are matrices. If this was a first order system with one input, what would be the dimensions of capital A? If this was a first order system, it would be 1 by 1. It would be a scalar. So it would be a scalar, as would capital T. If it was a second order system, then A always is square. It would be a 2 by 2. And you would simply scale every entry, all four entries in that 2 by 2 matrix by the sampling period capital T to give you AT. Now let's move one of those capital X of Z's to the right, or add capital X of Z to both sides of that equation. Here I had Z in the next to the bottom row right now in the display. You have Z times capital X of Z minus capital X of Z. I can move that to the other side by adding X of Z to both sides. And that's all I've done. And I've tried to illustrate that with this dashed red arrow. The next step that I want to perform is actually combine this vector, capital X, with another vector, ATX. And how am I going to do that? How am I going to combine capital X in these two terms? I want to factor out the coefficients, but the coefficients now are matrix coefficients. A is an n by n, 10 by 10 matrix, potentially. Then this 1 magically becomes the identity matrix that's 10 by 10. So that I can now factor those and combine this coefficient with AT. That's all I've done in this next line, is simply factored out or combined those first two terms on the right-hand side of the equal sign so that I can now factor out a common x vector, capital X of z. I'm still in the frequency domain. I still have z's floating around. I want to go into the time domain. But what will z times capital X of z look like in the time domain? What happens when you multiply by z? Z is an operator. What happens when you multiply, or if you've multiplied by z in the frequency domain and you want to go into the time domain, what does that look like in the time domain? Now we just have to increase the argument of n by 1. We've now put an advance in our argument. It's now little x of n plus 1. It's not hard to go from frequency domain to time domain in the state space representations. And hopefully this now is begging, you can see these hints with these curly brackets, that in fact we've now determined the system matrix phi in the discrete time forward numerical integration discrete equivalent approach. We've determined gamma, the input matrix. That's just B times T. And the output equation, we didn't have to change. H is actually C, J is actually D. Or we've now derived those functional relationships for the forward numerical integration discrete equivalent state space strategy. If I give you an A, B, C, D, you should be able to give me a phi, a gamma, an H, and a J if I say do this for the forward numerical integration approach. There are your formulas. You don't have to rederive anything. You just have to use these formulas. You just have to know what is A. That's your system matrix in the continuous time, and that now informs how big I is, the identity matrix. If little a is 3 by, if big A, we're on the U of A campus, if A is 3 by 3, what's I? It's 3 by 3. And you should be able to do that math. An identity matrix plus A times T. And that's phi. That's a little easier than this inverse Laplace transform of SI minus A inverse, but that was for the zero order hold equivalent. This is a discrete equivalent using numerical integration, but it's the same kind of idea. It's a discrete equivalent. Question? Does H always equal C? And now I want you, hopefully you came in on your inverted pendulum today, which means what? You hopefully have a helmet, because now strap your helmet on, because it's going to get a little bit more interesting to do the backward approach. And we'll see, maybe in that C, that H is not C. Sorry. So in the zero order hold equivalent, H equals C, and if we were using J, J equaled D. So in those two cases, it's correct. The zero order hold output equation had the same structure and the continuous time as the discrete time. The same for the forward. But now what we're going to do is strap on the helmet and figure out, because you already have looked at problem number 5 on homework number 4. And it didn't look like that, did it? It does not have that nice structure for phi, gamma, h, and j. It's a little more involved. So let's see where those involved formulas come from. And this is what you now might want to wake up and just write down so you can copy for homework number 4. Are we ready? Now what we want to do is move into the z domain for the backward rule, which means S now will be replaced by z minus 1 over tz. So let's do that. Now we have z minus 1 over tz times capital X of z is equal to the right-hand side, matrix A X of z plus matrix B E of z. Do you remember what we did in one of the first steps of this process before? We're now in the frequency domain for the discrete time setting. Let's clear that fraction on the left, multiplying both sides by capital T, Z. Now it's a little more complicated because now we're multiplying not by just a constant t, but an operator, or this complex frequency variable, z. But let's do that. We now have z minus 1, capital X of z, equaling ATZ X of z plus BTZ E of z. And now I want to combine some of these terms. Suppose I now want to combine, well, I could either combine or I could go into the time domain. It's kind of whatever you want to prefer, but let's just go ahead and go and combine this. I now have ZI, or let me do it this way. I minus ATZ times X of z. I've moved that ATZ on the right side of the equal sign to the left, and I'm going to push this capital X of z, the minus capital X of z on the left, I'm going to move it to the right and just drop down. Everybody okay with the algebra? No? This piece is right there with the I times z. The ATZ is AT with the z factored out, and it's now on the left, so I had to subtract that from both sides. And this 1 here gives rise to that one. So I did some shuffling. I'm doing a card trick, and I'm shuffling the cards on the table. But I haven't changed anything, have I? It's the same stuff on the table. Now, let's go into the time domain. And what does that look like? Can I say that that's x of n plus 1 minus at x of n plus 1 Now I'm going to do some more card shuffling. I'm going to bring that BT, ZE to the Z on the left-hand side, since they're all with the same time index. And if I do that, how does it come over? And what's left on the right-hand side? Do we see where those terms came from? I just went into the time domain and I actually slid that BTZE in the time domain to the left-hand side. So that's E advanced by 1, n plus 1 times a BT, and since it was plus BT on the right, it's minus BT on the left. And as you gain a little bit more comfort with these, that left-hand side looks kind of messy, doesn't it? One way that you can clean up a mess is to just relabel it. Just call it a mess. And the way I'm going to call it a mess is I'm just going to say that's W of n plus 1. I'm going to create a new variable. W, and that's now, what's the dimension of W? If X is a 10 by 1 vector, how big is, or what's the dimension of W? Has to be compatible. It has to be 10 by 1 also. So now, what have I actually done? Well, now I've actually created a new variable, W of n plus 1, and it's equal to X of n. And boy, is that going to be helpful. And we're going to use that later. So if I use it later, I might call it star. Now what I want to do is I want to find a W of n plus 1 equal something, some matrix times W of n plus some matrix times E of n. And then I'll have my dynamics. That's what I'm searching for in this magic trick, in this card shuffling, in this matrix shuffling. I defined then W of n plus 1 to equal X of n plus 1 minus AT X of n plus 1 minus BT E of n plus 1. If that's W of n plus 1, can you now write down W of n? We've done this before. If we had a linear difference equation, we could change the arguments of those indices by however many values we wanted, as long as we were consistent with how we changed them in every argument. What have I done between W of n plus 1 and W of n? I've just dropped a 1 in my argument. Can I do the same thing on the right-hand side? Now I can write W of n as simply X of n minus AT X of n minus BT E of n. And I can clean that up a little bit by saying, oh, that's I minus AT X of n minus BT E of n. And boy, that looks nice. I know you don't think so maybe, but that's a really nice looking equation. I now have W of n equaling some function of x of n and E of n. So I have an equation containing W of n, and that's what I needed on the right-hand side of a W of n plus 1 expression. I also have x of n, and I have E of n. The fact that W and E are functions of little n is great, and I also have x of n. I can now solve for little x of n, because do you remember my later equation? My later equation was W of n plus 1 is x of n. If I can now rewrite little x of n in terms of W of n and E of n, I'm home free. Everybody have their helmet on still? Don't want any concussions. You don't want to be going through a concussion protocol during the exam. All right. Where were we? Let's now solve that for little x of n. Little x of n now becomes I minus AT inverse W of n. So now I'm just going to multiply on the left of the left and right hand side by the inverse of I minus AT. And I now have plus I minus AT inverse. So I'm taking now the E of n to the other side, dt E of n. Now I have an equation of x of n in terms of W of n and E of n, and that's what I needed on the right-hand side of my equation for W of n plus 1. And that will give me a dynamic relationship, a state space relationship for this backward numerical integration discrete equivalent strategy in state space form. Here's the time for the later, which was W of n plus 1 was equal to x of n. That allows us now to write W of n plus 1 is equal to I minus AT inverse W of n plus I minus AT inverse BT E of n. Do you see how to now extract or identify the phi matrix? It's what's multiplying little w of n. There's the system matrix in the discrete time backward numerical integration strategy. So phi matrix in this case, the question was phi needs to be in front of x of n. Now what we're doing is we're actually changing the state variable. We're making it w. We're now having dynamics of w of n plus 1 equal some system matrix phi times w of n plus some matrix times the input. As long as we keep the input and the output the same, the state vector could be a little different. And in this case, it's w instead of x. But we know how to relate w and x if somebody wants x, don't we? If somebody wants x, you just give them w of n plus 1, and they have x. But behind the scenes, all we really need to worry about is w, its dynamics. What's the output equation? That's U of n is equal to C x of n plus D E of n. But now we can't write it in terms of x. We have to have the same state vector. So now the output matrix is not going to be C. What are we going to do? Well, now what we're going to do, and I'll let you do this on your own. I don't want you to not have to do anything tonight. When you go home, I want you to have something to do. Now you can replace that little x of n with that right-hand side. And now you have U of n equaling some matrix times W plus some other matrix times E, and that will be your H and J matrices in the discrete time representation. That's problem 5. And I didn't think I could write that in an email very effectively. Because 1, you didn't have your helmet on if you were reading your email. And 2, you couldn't see all the card shuffling. What if somebody wants x of n? You just hand them W of n plus 1. Questions? Do you know how to use this? You don't have to rederive it. You've seen it performed. You've seen the magic performed. You now need to be able to apply it. Which means if I say, give me a state space representation using the backward numerical integration discrete equivalent technique, all you do is now you have to find the H and the J formulas. You already have the phi and the gamma, and now you just need A, B, C, and D, and T, and you're done by combining them in this way. You might have to perform a matrix inverse, but that might be easier than calculating e to the capital AT. But that's a different one. That's a zero-order hold equivalent. Here's a table summarizing that. I didn't tell you to take your helmet off, but now I have it in columns. The leftmost column is the phi, the gamma, the H, and the J. So now if I tell you backward, whoops, you'll read down the middle column. And you'll just use those formulas to get the phi, the gamma, the H, and the J. Now you should be thankful we're not driving that rightmost column. But that's the trapezoidal relationship. What do you need? You need a 2, because you're going to have 2's floating around, and you're going to need to take the square root of capital T and use T by itself. But if I said, give me the trapezoidal numerical integration, you now know how to apply that formula, I would expect. It involves an inverse. It involves a multiplication of matrices. It's a little bit more involved, but it's doable. Question? So the question was, do we ignore the fact that, now I have to jump back, but in this backward approach, we said that W was in fact, W of n plus 1 was x of n. So you would have to know And in this case, you would define a new vector in the rightmost column for the trapezoid. So you don't ignore that, especially if somebody needs to know what's my state vector x, the original state vector x. You would have to know the relationship of relating in the middle column. You know it. It's w of n plus 1 is equal to x of n. So you can't just ignore that unless somebody says, I could care less what's going on in your machinery. I just want to know the input-output behavior of this operation. And you can give them that without telling them what's going on in your state vector in any of these columns. Did that answer your question? Question? So the question was, on the exam, how much of this are we going to have to derive? Yes, I think I'll just have you derive the trapezoidal for exam number 2, since you asked the question. Actually, I just want you to be able to use this table. You don't have to derive anything. I give you credit for staying awake during the derivation. So if anyone's asleep, maybe I'll take that down. But I'm assuming what you want to be able to do is understand what this means and how to use it. Is that clear for the exam? So you will need to have this on one of your pages of notes so that you can apply it. But you don't have to rederive it. But you now know if somebody says, oh, I need the forward, oh, and it's in a state space representation. Isn't this easier actually to perform this mechanics than finding the z transform of g of s over s if you had a fifth order transfer function? I think so. You now just have to do some fifth order, maybe a fifth order inverse, but you've got a calculator right here. If you're listening, you didn't see me pointing to my head. That's where your calculator resides. But you're getting this now in this state space representation. Other questions? Let's go through one more discrete equivalent, which is the pole zero mapping. So how many different discrete equivalent types have we covered? Zero order hold, and that has a hold in front of the dynamics. That's when you apply it, when you want to incorporate that hold and your system behavior. The other two, which is the numerical integration and the pole zero mapping, those are under scenario number 1, where you don't have to worry about incorporating that hold mechanism into your discrete equivalent. So the hold is essentially, the hold device is really converting this sequence of numbers into an analog or a continuous waveform. And we're doing it via a zero order hold, so we're just holding it constant. So the hold device is really introducing some dynamics because it's changing this sequence of numbers into a continuous signal. And we integrate that or incorporate that into the discrete time representation of that model. Here, with the pole zero mapping or the numerical integration, we could take a string of numbers and boom, pop out an answer. We don't need a continuous waveform in this process. So these are for like controllers or filters. That's why we might want scenario number 1. We don't need to worry about the hold device. Here's the strategy, or here's the idea. We map poles of H to poles of H of Z. We map zeros of H of S to zeros of H of Z, and those could be finite and infinite zeros. And we match the gains. Low frequency gains if it's a low frequency transfer function, high frequency gains if H of S is like a high pass filter. If it's a band pass, maybe we match the gains at a particular frequency value in the band, in the pass band. And one of the nice things is this actually preserves stability. If you have poles of h of s in the left half plane, those have negative real parts. And where do those map through this z equal e to the st? Inside the unit circle. E to the minus something t. Those are inside the unit circle. We preserve stability. Let's walk through this. Here's the approach. First, we probably want to factor capital H of S into the zero factors and pole factors so we know what we're mapping. So we factor H of S into pole and zero factors. Once it's factored, now we can start playing with mapping the poles and zeros. So we could do it in either order, but here let's just say for step 2, let's map poles of H of S to z-plane poles using z is equal to e to the st. Suppose we now had just a simple pole factor, S plus A, and it's a pole factor, it's in the denominator. We can now say that we have a pole at the value of S where that denominator vanishes, which is at S equal to minus A. S equal to minus A mapped through Z is equal to e to the st now says that I have Z is equal to e to the minus AT. And if I want that to be a pole factor, I would have my factor, so this could be a zero factor, but if I make it a pole factor, I can make it a pole factor by putting it in the denominator. And the value of z that causes that to vanish is e to the minus AT. If I plug in or replace z in this formula with e to the minus AT, that's the root of that factor. Now, this actually holds for poles and zeros, so can I just say, what if I have a complex root? What if I had a complex root that was maybe S equal to minus A plus JB? And if I have plus JB, I have to have its conjugate if I have real coefficients. So now I have complex roots at minus A plus and minus JB. How does that map? Or what kind of a factor do I have there? And this is a hint for another homework problem. Maybe. Well, we're doing the mapping the same. Z is equal to e to the st. And just replace S with one of the, I'm just going to use one of those, but we have the conjugate of that. But in this case, let's say it's e to the minus A plus JB. I'll use the one in the positive half plane upstairs times t. Or this is now, and now I can slide that scalar t through both pieces in my exponent, and I have minus AT and I can separate those two pieces into two terms. And now I actually have a polar representation of that complex pole. I have a magnitude represented by e to the minus at, and I have an angle represented by e to the j bt. I can say this piece is r, and this piece is e to the j theta. Or I now have one of my roots is r e to the j theta. And you can find those once you're given minus a plus jb. But once I have this, now I just have to remember Euler. E to the j theta, cosine theta plus j sine theta. Or that's now r cosine theta plus r or jr sine theta. And I could say that that's some real part. The polar, now I'm going to write that polar in rectangular form. And the rectangular form has a real part, r cosine theta, and it has an imaginary part that I'll call z sub I. And now, if somebody gives me a complex pole pair, a pair, plus and minus jb, now I can write that as z minus z sub r squared plus z sub I squared, and that's in the denominator if it's poles, and it's in the numerator if it's zeros. And that's how you would handle complex roots versus real roots. Pardon? So the conjugate is buried in here because this is a quadratic. If you now find the roots of this, you'll find the roots of this are at z sub r plus and minus jz sub I. Because it's a quadratic and you have two roots and they're complex. The real part's z sub r and the imaginary part is z sub I. So I would say go home tonight and convince yourself that this, when you solve it, ends up being or giving rise, or you can plug in z of z sub r plus jz sub I and z sub r minus jz sub I, and it will make that go to 0, both cases. Where were we? We were still on step 2, which was mapping the poles, and I injected this complex root thing, so you could use this in step 2 or step 3 if you have complex roots. Step 3 is the map the finite zeros of h of s to z-plane zeros using the same relationship. Z is equal to e to the st, and s could be real or complex. And you know how to use both. As an example, suppose the numerator was some k, s plus b, what's the zero factor going to look like in the z domain? The gain's probably going to be different, so I'll say k bar, but what's the factor going to look like? That's now how you would map that real pole at minus b into its numerator factor to give me a 0 factor. Now let's get into the fun part, which are the infinite zeros. The infinite zeros of h of s are, and now let me put in parentheses, typically, for this first, the original version of this presentation, typically mapped to zeros at the point z equal minus 1. Suppose I gave you s plus b over s plus a. How many infinite zeros do I have? How many zeros at infinity do I have? Okay, I'm going to allow you 3 options. 1, 0, that'll be this, 1 or 2. Okay, show of hands and you can say 0, 1 or 2. 1, 2, 3. How many zeros at infinity do I have? What's the pole 0 excess? How many more poles do I have than zeros? It's 1 minus 1. So the pole 0 excess is 0. I'm going to have to quit doing that. So now I have 0, so I don't have to worry about any factors of z plus 1 for that example. So let's play a little with it. Suppose let's now add some more poles. What's the pole 0 excess there? How many more poles? So the pole 0 excess, how many more poles do I have than, how many finite poles do I have? 2. How many finite zeros do I have? 1. What's my pole 0 excess? 2 minus 1 is 1. So now I would have a z plus 1 factor in my numerator and my discrete equivalent. So let's put up this a little bit. What's the number of finite zeros now in this transfer function? I have 2. What's the number of infinite zeros? Now you need to show me more fingers, don't you? How many poles do you have? So the denominator's 5th order. The numerator is 2nd order. The pole 0 excess is that difference, 5 minus 2. You now have 3 zeros at infinity. And that means that you would map, in the typical case, that means you would have z plus 1 cubed as a numerator factor. The pole 0 excess, So the pole zero excess, and this is something that I would have barked at you all during 441A, 541A, was the pole zero excess, because it has a lot of meaning in that scenario. But here, we just need it to know how many poles do I have minus the finite zeros, and that gives me the number of, or my pole zero excess. And that's actually the same as the zeros at infinity. Now, why do we map them into this factor z plus 1? Why is z equal to minus 1 like infinity in the z domain? So let's see what we can come up with. Suppose here's our S-plane, and I wanted to know the frequency response of a transfer function. Here's the real values of S. Here's the imaginary value of S. If I want the frequency response of H of S, where do I walk? Where do I live in the frequency domain? If I want to find the frequency response, if I wanted to plot the Bode plot, how would I evaluate, or where would I evaluate this H of S? There's some place in the S domain that we would walk. If I want the frequency response of a transfer, of a system, of a transfer function, H of S, where do I evaluate that? What do I set S equal to? J omega. So I'm walking up the imaginary axis. That gives me the frequency response. H of S would be represented, let's say, by some poles and zeros, and now I would just walk up this axis to get the frequency response. So I would evaluate this H of S at S equal to J omega, and that would give me my H of J omega. That's the frequency response for a continuous time system. What does that look like in the discrete setting? Well, we just go back to our friend, which is this mapping relationship. Z is equal to e to the st. Here's our z-plane. And if z is equal to e to the st, and we are using the same frequency response, we replace s with j omega. Z now becomes e to the j omega t. What's the magnitude of that? Now just recall Euler. If you don't see it, you just you say, oh, Euler says cosine omega t plus j sine omega t, and I want the magnitude of that complex number. So now I have cosine squared plus sine squared. That's equal to 1, no matter what omega t is. That has a magnitude of 1. Which means now that I'm on this unit, that's supposed to be a unit circle. So I'm at 1, I'm at minus 1, I'm at j1, I'm at minus j. Z equal e to the j omega is somewhere on that unit circle. Where's DC in the S-plane? Where's zero frequency? Here's DC is right at S equal to 0. Where is that in the Z-plane? There's DC. Now as we walk up the imaginary axis, do you see that this angle just starts growing from 0? If I'm now measuring my angle from the origin, and I'm looking straight out into the positive real line in the z-plane, now I just start looking over, or as that omega t increases. And I'm going to now just start walking around to get the frequency response. What happens? Well, if I'm here, that's basically the same as down there because they're conjugates. And if I keep having these twins, as far as I can go in this diagram is over to that point. That's as high as I can get in frequency, is all the way over to that. And what is that point? Well, that's -1. Or what's that angle? Or you could say, if I was walking up here at different frequencies, what's the highest frequency I can get to that makes any sense when I've sampled that continuous time signal? If I'm sampling at an omega sub s, what's the highest frequency I can actually identify in a sampled signal sampled at omega sub s? Nyquist. Do you remember Nyquist or not? But now if the highest frequency that you can ascertain in a sampled waveform is half the sampling frequency. So the highest frequency you can find is omega sub s over 2. What's omega sub s? 2 pi f sub s. Or that's 2 pi over t. And now I just said the highest frequency that we can discern in a sampled waveform is omega sub s over 2. Well, what's omega sub s over 2 in terms of capital T? Isn't it just pi over t? Now, what happens when we plug in omega equal to pi over t in our relationship relating z domain to s domain? This is now e to the j omega sub h is pi over t times t. What's e to the j pi? Go back to Euler. Cosine pi plus j sine pi. What's sine of pi? We're getting awful close to pi day. We need to know these formulas. Sine of pi, 0. Cosine of pi, -1. So e to the j pi is -1, or you could say, well, that's 1 at an angle of pi, or it's 1 at an angle of 180 degrees. So now this point of -1 corresponds to omega equal to omega sub s over 2, which is pi over t. So that's the highest we can get to. That's infinity in the z domain. That's as high as we, and that's why if we wanted a factor, the zero factor associated with z equal to -1 is what? What factor has a root at when z is equal to -1? We can just add 1 to both sides of that equation and we get z plus 1 is equal to 0, and that's actually the factor we need. So this factor, z plus 1, has a root when z is equal to -1, and that's why all of these zeros at infinity we want to map to factors that are equal to z plus 1. And I've tried to justify where that infinity comes from. We're doing the frequency response, which means we're walking around the unit circle, and as high as we can get in frequency is half the sampling frequency, and we found that that was equal to pi, or e to the j pi, or minus 1. Now, I gave you some additional material, didn't I, in an email today? It's at the bottom of Unit 4. It says hints for solving these relationships, and it's really trying to justify why your answer might be different than MATLAB. MATLAB maps one fewer 0 at infinity to this z plus 1 factor. They make the gains, maybe the constants aren't the same, but the gain of the overall transfer function better be the same at the same frequency. Thank you. Good luck on your exam. I'll see you either in a few minutes or at the exam.